Number 1. Davemaoite, the impossible mineral hauled up inside a diamond. Picture a single diamond pulled from the red earth of the Arapa mine in Botswana, the largest diamond mine on the planet by area. To the eye, it is unremarkable. But locked at its center is a green speck a few micrometers across, smaller than the width of a single human hair. That speck should not exist. It is a mineral called Davemaoite, a form of calcium silicate perovskite, and it is only stable deep inside the earth, in the lower mantle, somewhere between 660 and 900 kilometers beneath your feet. No drill has ever reached that layer. No probe has ever sampled it, and yet a mining crew carried a piece of it to the surface without knowing they had done so. In 2021, the mineralogist Oliver Chauner of the University of Nevada, Las Vegas, confirmed Davemaoite as a genuine natural mineral, publishing the result in the journal Science. He named it for the high-pressure geophysicist Ho Kwang Mao, known to colleagues as Dave. Here is the strange part. At the pressure you feel right now, calcium silicate perovskite is unstable. Released from the deep earth, it would normally collapse into a different structure within moments. The only reason this grain survived is that the diamond around it acted as an unbreakable pressure vessel, holding it at the conditions of its birth. To identify something so tiny, Chauner's team used synchrotron X-ray diffraction, a technique that can read the crystal structure of an inclusion-only microns wide. What they confirmed was remarkable. Davemaoite is thought to make up 5 to 7% of the entire lower mantle by volume, making it one of the most abundant minerals on Earth, even though no human had ever seen it. It also concentrates the radioactive elements uranium, thorium, and potassium, whose decay helps drive the heat engine of the planet. The diamond itself formed under pressures above 20 gigapascals, more than 200,000 times the pressure of the air around you. It was blasted upward by a kimberlite pipe, a volcanic conduit that fires deep material toward the surface, possibly faster than the speed of sound. The Arapa pipe erupted about 93 million years ago, while dinosaurs still walked the earth. Consider this. The deepest hole humans have ever drilled reached only 12.2 kilometers. This mineral came from more than 50 times deeper. So if a diamond can smuggle the mantle to the surface, what else have miners pulled up without ever realizing what they held? Number 2. Carbonado, the black diamond that may have formed in a dying star. If Davemaoite is the deepest thing on this list, Carbonado may not come from this world at all. Carbonado is a porous black polycrystalline form of diamond, the toughest natural diamond known, built from countless microscopic diamond crystals fused together. It is found in only 2 places on Earth, the river gravels of Bahia in Brazil, and the deposits of the Central African Republic. The name comes from the Portuguese word for burned, given by 18th century Brazilian miners who pulled the dark stones from the gravel. Everything about Carbonado breaks the rules. Ordinary diamonds form in kimberlite pipes deep in the mantle. Carbonado has never once been found in a kimberlite pipe. It has been dated to between 2.6 and 3.8 billion years old, among the oldest diamonds known. And its 2 homes, Brazil and the Central African Republic, were joined together when the ancient supercontinents Gondwana and Rodinia existed, which explains why the deposits now sit on opposite sides of the Atlantic. This is where the physicist Stephen Hagerty of Florida International University proposed something extraordinary. He argued that Carbonado may have formed in a supernova, the explosive death of a star, out in interstellar space before arriving on Earth as a massive meteorite. The evidence he and others point to is genuinely strange. Carbonado contains hydrogen. It shows trace element patterns resembling interstellar dust. Its luminescence is consistent with long exposure to cosmic radiation, and its porous, sponge-like texture looks like material condensed from a cooling cloud of gas, not crystallized inside solid rock. There are competing theories, and good scientists hold them. Some argue Carbonado formed through the radioactive decay of uranium and thorium in the early crust. Others suggest it was shock formed by a meteorite striking the Earth. What pushes against a deep Earth origin is telling. Carbonado lacks the mantle mineral inclusions that ordinary diamonds always carry. And no source rock for Carbonado has ever been found anywhere. Unlike every other type of diamond, the stones can be enormous. The largest, called the Cerrejón, found in Bahia in 1895, weighed about 3,167 carats, more than 600 grams. Carbonado is so tough it was once used industrially, and Carbonado-tipped drills helped bore the Panama Canal. So here is the unsettling thought. If Haggerty is right, Carbonado is the only mineral that humans routinely mine and use that was forged in the death of a star. From the unreachable mantle to a dying sun, and now we come back down to bones. Number 3, the Cambridge Coprolite diggings, where Victorians mined a graveyard for fertilizer. In the farmland of Cambridgeshire, England, lies a thin band of rock called the Cambridge Greensand, sitting at the base of the Great Cretaceous Chalk. It is packed with dark, dense, green-gray nodules, and in the middle of the 19th century, those nodules became the center of a strange industrial boom. They were called coprolites, a word coined by the geologist William Buckland in 1829 to mean fossil dung. In truth, many of the nodules were not dung at all, but phosphatized bones, teeth, and reworked fossils from a Cretaceous seafloor about 100 million years old. The boom began when the chemist John Stevens Henslow, the very man who mentored Charles Darwin, recognized around 1843 that these nodules were rich in phosphate and could be turned into fertilizer. Treated with sulfuric acid, the crushed nodules yielded superphosphate, exactly what a hungry, industrializing nation needed to feed its fields. Between roughly 1850 and 1880, thousands of laborers dug shallow trenches across the countryside, stripping away the overburden to follow a bed only centimeters thick. The work was wet, hard, and seasonal, but it paid relatively well for the era, and it created boomtown conditions across the region. As the diggers worked, they hauled up the teeth of marine reptiles, the teeth of ancient sharks, and the scattered bones of a vanished sea. Much of that material flowed into scientific collections, including the Sedgwick Museum in Cambridge. The paleontologist Harry Govier Seeley studied the pterosaurs and reptiles of the Cambridge Greensand through the 1860s and 70s, building our early picture of Cretaceous life from material a fertilizer industry threw up as a byproduct. There is a darker side. The acid treatment factories produce choking fumes and toxic runoff, almost entirely unregulated, poisoning local water and air. And there is real fossil dung in such deposits too. Genuine coprolites can preserve undigested bone, scales, and fish remains, letting scientists reconstruct what ancient predators actually ate, the very insight Buckland first championed. The British coprolite industry collapsed in the 1880s when cheaper phosphate imported from overseas deposits undercut the price. But while it lasted, it did something almost no other industry has ever done. It took a Cretaceous death assemblage, a seafloor strewn with the bones and waste of dead animals, and ground it directly into the wheat that fed living people. From grinding bones into bread, we turn now to a death frozen in the very act of giving life. Number 4. The Holzmaden Quarry, and the mother frozen in the act of giving birth. In the town of Holzmaden in southwestern Germany, quarry workers have for centuries split a black, oily rock called the Posidonia shale, cutting it for roofing slate and flooring. The shale dates to the early Jurassic, the Torsian stage, between about 182 and 174 million years ago. And when a worker splits a fresh slab, what emerges is sometimes almost unbearable to look at. The Posidonia shale formed on an anoxic seafloor, a seabed with almost no dissolved oxygen, where nothing could scavenge a corpse and decay slowed to a crawl. The result is one of the finest fossil deposits on Earth, a place where animals are preserved whole. Holzmaden is famous above all for the ichthyosaur Stenopterygius, a dolphin-shaped marine reptile that grew to 3 or 4 meters long. Here, the fossils preserved not just bone, but the outline of the body itself, the fleshy dorsal fin and the fish-like tail fluke that no skeleton alone would ever reveal. And then there are the births. Several Holzmaden specimens preserve female ichthyosaurs in the act of giving birth, with tiny embryos emerging tail first, exactly as a dolphin is born today. One famous slab shows embryos still inside the mother and one half emerge from the birth canal, both dead, both held in the rock for 180 million years. These fossils proved beyond any doubt that ichthyosaurs bore live young rather than laying eggs. But how did such a scene form? Here, the scientists divide. The mainstream view is that some of these females genuinely died in labor, a difficult birth ending in the death of mother and young together. A competing interpretation argues the babies were not being born at all, but were pushed out after death by the gases of decomposition bloating the carcass on the seafloor. Both readings are taken seriously, and the truth may differ from fossil to fossil. We owe much of this to one family. Bernhard Hoff, born in 1866, pioneered the careful preparation that first revealed these soft tissue outlines in the 1890s. He proved the dark halo around the bodies was not a stain but carbonized flesh, settling long arguments about what these animals looked like. Later studies even found evidence of blubber and skin pigment, showing ichthyosaurs were warm-bodied and counter-shaded, dark above and pale below, just like a modern dolphin. The poisoned, airless water that preserved them so perfectly is itself a clue, pointing straight to the forests that once changed the very air above the sea. Number 5, coal balls and the petrified forest that loomed in the mine ceiling. Coal is a forest. We rarely think of it that way, but every lump of coal is the crushed carbonized remains of ancient swamp plants. And inside many coal seams, miners have hauled up something extraordinary, round mineral lumps called coal balls. A coal ball is a concretion that preserves the original swamp plants in 3 dimensions, cell by cell, before the pressure of burial could flatten them. They form when carbonate minerals and sometimes pyrite soak into the peat and entomb the tissue while it is still intact. They were first described in Britain in 1855 by Edward Binney and the botanist Joseph Dalton Hooker. Decades later, scientists developed the peel technique, refined in the 1920s and 30s, in which a cut surface is etched with acid and a thin acetate film lifts away a perfect imprint of the ancient cells. Through coal balls, we can study the anatomy of a 300-million-year-old plant down to its spores and reproductive organs. This matters enormously because ordinary coal destroys all of that detail. The coal balls are windows into the living swamp. That swamp belonged to the Carboniferous, the Coal Age, roughly 359 to 299 million years ago, when vast equatorial forests laid down the coal that would one day power the Industrial Revolution. The dominant trees were giant club mosses, Lepidodendron and Sigillaria, towering 30 to 50 meters tall. Their bark carried a distinctive diamond-shaped scar pattern, so reptilian in appearance that the public has long mistaken it for fossilized snake or dinosaur skin, but the forest in the coal mine was not only a wonder, it was a killer. Miners regularly found large fossil tree casts embedded in the roof and walls, entire trunks preserved in place. The most feared were called kettle bottoms, fossil tree stumps wrapped in a slick rind of clay. Because the rind let them slide free of the surrounding rock, a kettle bottom could drop without warning from the ceiling, crushing the men below. Some miners spoke of the forest taking its revenge for being dug up. The forest came with giants of another kind. Carboniferous swamps hosted Arthropleura, a millipede relative up to 2.5 meters long, and Meganeura, a dragonfly relative with the wingspan of a hawk. Their size was fueled by an atmosphere possibly 30 to 35% oxygen, far above today's 21%. Around 305 million years ago, the Carboniferous rainforest collapse fragmented these forests as the climate dried. From a forest beneath a city's coal fields, we turn now to extinct beasts found beneath a city's streets. Number 6, the gypsum mines of Montmartre and the beasts that proved extinction is real. Beneath the hill of Montmartre in Paris runs a honeycomb of old mines. The hill is built largely of gypsum, mined since Roman and medieval times. And when that gypsum is heated and ground, it becomes plaster. The very plaster that gave the world the phrase plaster of Paris. The gypsum itself is Eocene, between about 34 and 38 million years old, laid down in the evaporating lagoons of an ancient sea that once covered the Paris basin. Into these mines, around 1798, came Georges Cuvier, the founder of comparative anatomy. The quarrymen had been pulling delicate fossil bones out of the soft gypsum and selling them to naturalists, and Cuvier set about reconstructing the animals they came from. He described extinct mammals such as Palaeotherium and Anoplotherium, creatures unlike anything alive. Using what he called the law of correlation of parts, he argued that the whole form of an animal could be predicted from a single bone, and a near-complete Palaeotherium skeleton from Montmartre later proved him right. The deeper consequence was philosophical. By showing that these animals matched nothing living anywhere on Earth, Cuvier established extinction as a scientific fact. Before him, many believe no species could ever truly vanish. After him, the past became a graveyard of vanished worlds. He published these findings in his landmark work on fossil bones beginning in 1812. Cuvier read even more in the rock. Working with the geologist Alexandre Brongniart, he mapped the layered strata of the Paris Basin and noticed that the layers alternated between marine and freshwater deposits, proving the basin had flipped between sea and lake again and again. This led him to catastrophism, the idea that sudden revolutions had repeatedly reshaped life. And by matching distinct fossil faunas to distinct layers, he and Brongniart pioneered biostratigraphy, the dating of rock by the fossils it contains, a tool still central to geology today. There was a cost to all this mining. The over-quarried hill was left riddled with dangerous voids, and the resulting collapses and instability would go on to shape Parisian building codes for generations. But the legacy is hard to overstate. The science of paleontology itself, the very idea that the Earth holds a succession of lost worlds, was assembled from bones hauled out of plaster mines beneath a living, breathing city. From a single dead world under Paris, we move now to an entire dead rainforest, ripped open by one of the largest mines on Earth. Number 7. The Cerrejón coal mine and the lost rainforest at the dawn of our world. In the hot, dry La Guajira region of northern Colombia sits Cerrejón, one of the largest open-pit coal mines on the planet. As its draglines and shovels strip away rock, they have exposed something the world had never seen, one of the earliest tropical rainforests frozen in the rock of the Cerrejón Formation, between about 60 and 58 million years old. That places it in the Paleocene, just a few million years after the asteroid impact that ended the age of dinosaurs. This is a record of recovery, of how the tropics rebuilt themselves after the worst day in the history of complex life. And the animals that returned were monstrous. The most famous is Tiernoboa cerrejonensis, the largest snake that has ever lived, an estimated 13 meters long and weighing over 1,100 kilograms. It was described in 2009 by a team including Jason Head, Jonathan Block, and Carlos Jaramillo. Its sheer size is itself a thermometer, a cold-blooded animal that large could only survive in extreme heat, implying mean annual temperatures of 30 to 34 degrees Celsius, a super greenhouse tropics far hotter than today. Titanoboa did not rule alone. The mine yielded Carbonames, a giant freshwater turtle with a shell about 1.7 meters across, described in 2012. It produced deirosaurid crocodile relatives such as Acherontosuchus, river predators that may have been Titanoboa's prey, or its rivals, and it preserved the forest itself, fossil leaves, fruits, and pollen, revealing a jungle of legumes and palms, the same plant families that dominate the Amazon today. How did Titanoboa live? Here, the scientists differ. The mainstream view holds it was largely aquatic, an ambush predator lurking in rivers, hunting giant fish and crocodilians. A competing interpretation pictures it as a terrestrial constrictor, crushing large prey on land like a colossal anaconda. The debate is unresolved and the truth may lie between the two. The work of paleobotanists like Carlos Jaramillo and Scott Wing showed that plant diversity crashed at the extinction and then slowly rebuilt over millions of years, and that this hot, high carbon dioxide world is a possible window into our own warming future. There's a deep irony here. The coal Cerrejón mines is the compressed peat of these very rainforests, so the machinery extracts the ecosystem and exposes it in the same stroke. And once again, it was a poisoned, oxygen-starved environment that preserved the next haul on our list, just as it did at Holzmaden. Number 8. The Kupferschiefer, an entire Permian sea sealed inside copper ore. Across Central Europe runs a thin black layer of rock called the Kupferschiefer, the copper shale. It is rarely more than 30 to 60 centimeters thick, yet it has been mined for copper and silver for more than 800 years. At Mansfeld in Germany, copper mining in this layer began around the year 1199 and continued until 1990. For 8 centuries, miners broke open this rock for metal, and in doing so, they opened a Permian seabed page by page. The Kupferschiefer is between about 255 and 257 million years old, deposited in the Zechstein Sea, a body of water that flooded a vast basin across what is now Germany and Poland in the late Permian. And it is famous for its fossils. Exquisitely flattened fish such as the ray-finned Palaeoniscum and the shark relative Genasa, along with reptiles, amphibians, and plants washed in from the land. The fish are often coated in shimmering metallic films of silver and copper, giving them an eerie, iridescent sheen prized by collectors. The reason the fossils and the metals occur together is chemistry, and it is grim. The Kupferschiefer formed under anoxic, hydrogen sulfide-rich bottom water, a stagnant, poisoned sea where aerobic life could not survive. In that lethal water, bacteria-reducing sulfate caused metals, copper, lead, zinc, and silver to precipitate as sulfides into the organic rich mud. The same poison that killed the fish and preserved them is the poison that concentrated the ore the miners came for. This wealth shaped history. The metal riches of Mansfeld were tied to the family of Martin Luther, whose father ran copper smelting operations there. The landscape is still dotted with conical heaps of mine waste. And in Poland, the same horizon hosts the giant Lubin-Sierosiewicz deposits, among the largest copper sources in Europe, mined today by the company KGHM. But the most haunting fact is the timing. These fish died just before the end Permian mass extinction, about 252 million years ago, the greatest dying in the history of life, when as much as 90% of marine species vanished. The stagnant, oxygen-starved sea that preserved the Kupferschiefer fish is a small-scale preview of the global ocean anoxia that scientists believe helped drive that catastrophe. In the copper ore, miners hold a snapshot of the world on the edge of its worst extinction. From a Permian sea turned to stone, we turn now to flesh that never turned to stone at all. Number 9. The Klondike Goldfields, where gold mining keeps resurrecting the Ice Age. When the Klondike Gold Rush drew tens of thousands north between 1896 and 1899, no one expected the diggers to become accidental paleontologists. But placer gold mining in the Yukon and interior Alaska means thawing frozen ground, blasting away ice-cemented silt called muck with water cannons, and that muck is full of the Ice Age. Again and again, the dead come out intact, with skin, hair, and flesh still on the bone. The most famous is Blue Babe, a near-complete mummified steppe bison found by gold miners near Fairbanks, Alaska, in 1979. It is about 36,000 years old, and its skin had turned a strange blue from a coating of vivianite, an iron phosphate mineral that forms in oxygen-poor ground. The paleontologist R. Dale Guthrie of the University of Alaska Fairbanks studied it and read its death in its wounds. Claw and bite marks showed that American lions had killed the bison in autumn before it froze solid and was sealed away. To celebrate the find, Guthrie's team famously cooked a piece of Blue Babe's neck into a stew and ate it, reporting it was edible, if tough and earthy. Blue Babe is not alone. In 2016, gold miners near Dawson City in the Yukon uncovered Jur, a mummified wolf pup about 57,000 years old, named in the hen language of the local Klondike First Nation. It preserved fur, skin, and even the contents of its stomach, which showed a surprisingly aquatic diet. Then, in 2022, a Klondike gold miner working Eureka Creek struck something in the frozen ground and stopped his machine. It was Noon Cho Ga, a near-complete baby woolly mammoth, over 30,000 years old, one of the best preserved ever found in North America, and the Klondike honored the discovery with a ceremony. All of this comes from the Mammoth Steppe, a cold, dry, grassy world that once stretched across the entire northern hemisphere, feeding mammoths, bison, horses, and the lions that hunted them. The frozen silt acts like a natural refrigerator, sealing carcasses in airless cold for tens of thousands of years, preserving hair, organs, gut contents, and even DNA. Today, the paleontologist Grant Zazula works hand-in-hand with Yukon gold miners to recover what they find, because nearly every discovery happens on an active claim. But there is a race against time, because the same warming that thaws the ground also rots the carcasses it exposes. From flesh in the frozen north, we turn to teeth pouring out of a Florida dragline. Number 10. Bone Valley, where a single dragline bucket mixes sea monsters and land giants. In central Florida lies a region so full of fossils it is simply called Bone Valley. It holds one of the world's richest phosphate deposits, mined since the 1880s, and the name comes straight from what the mining churns up. Enormous electric drag lanes strip away the overburden and dig into the phosphate-rich layer called the matrix, which is then washed to separate the phosphate from sand, clay, and a torrent of fossils. The deposits range from the Miocene to the Pleistocene, roughly 12 million to 10,000 years old, and they have been reworked again and again, mixing fossils of wildly different ages into the same layer. So a single dragline bucket can lift the past in a jumble. Out of it tumble the teeth of Otodus megalodon, the largest macropredatory shark that ever lived, some teeth more than 17 centimeters long. Megalodon reached an estimated 15 to 18 meters in length and ruled the seas from about 23 million to 3.6 million years ago. And mixed in with those ocean predators come the giants of the land, the molars of mastodons and mammoths, the bones of giant ground sloths and armored glyptodonts, ancient horses, camels, and the ribs of dugongs. This strange marriage of sea and land reflects Florida's history, a peninsula repeatedly drowned and exposed as sea levels rose and fell over millions of years. The reworked deposits concentrate the densest fossils the way a sluice box concentrates gold, producing bone beds of staggering richness, and the famous Peace River cuts right through them. This is not a museum dig. Florida supplies a large share of the world's phosphate fertilizer, so this is heavy industry, and it carries an environmental legacy of clay-settling ponds and towering gypsum stacks. The deposits even contain naturally occurring uranium and radium, raising real concerns about radioactivity. The fossils themselves are usually stained a deep brown or black by phosphate and iron during their long burial. Why did the great shark vanish? The mainstream view holds that Megalodon went extinct around 3.6 million years ago as the seas cooled, its prey shifted, and competition rose, possibly from the smaller, faster ancestors of the great white shark. A more speculative reading wonders whether the rise of nimble new predators simply doomed the lumbering giant. Either way, the teeth keep coming, hauled up by the millions in the search for fertilizer, 10 hulls now, and one pattern beneath them all. The question is what that pattern means. Step back from the individual hulls and a single fact stands out. Mining is the largest deliberate earth-moving force that humans have ever wielded. In many regions, it moves more rock in a year than natural erosion does, and unlike a careful scientific excavation, it cuts straight down through time, exposing in a few years what nature would take millions of years to reveal. That is why mining keeps colliding with deep time. It is, without meaning to be, a planetary scale survey of the past. What makes the pattern so rich is that different commodities open different windows. Diamonds sample the unreachable mantle. Coal samples the ancient forests and the swamps that fed them. Phosphate samples old nutrient-rich seas. Gypsum captures evaporating lagoons. Copper shale records a poisoned ocean. Frozen muck preserves the ice age in flesh. Each thing we dig for is a key to a different chapter. And the deeper the mine, the older and stranger the haul tends to be. A kimberlite pipe can reach hundreds of kilometers down for diamonds. A coal seam reads as a single drowned landscape. A phosphate bed is a sea concentrated into a few rich layers. No single research budget could ever fund sampling on this scale, yet industry does it every day in pursuit of profit. There is a deeper reason these two pursuits keep meeting. The very conditions that create good ore often create good fossils. Anoxic, chemically hostile, oxygen-starved settings concentrate metals and at the same time prevent decay. The same poison that builds a copper deposit can preserve a fish in perfect detail. Wealth and memory lie together in the rock. And so the miner, not the scientist, is almost always the first human to break the seal. Whether it is a speck of mantle in a diamond, a kettle bottom in a coal roof, or a bison in the frozen north. But for everything that is found, we are left with an uncomfortable question. How much passes through the crusher unseen? To understand why these hulls exist at all, you have to understand a paradox. The destruction of a body is driven mostly by two things, oxygen and scavengers. Remove both, and flesh, bone, and even cells can endure for unimaginable spans of time. Nearly every hull on this list owes its survival to an environment hostile enough to halt decay, and each one preserves a different kind of information. Consider the methods. An anoxic seafloor, as at Holzmaden and in the Kupferschiefer, kills the scavengers and starves the bacteria, preserving shape and even soft tissue. Euxinia, water saturated with hydrogen sulfide, is lethal to aerobic life and a powerful preservative. Permineralization, the process behind coal balls and petrified wood, infills and replaces tissue with minerals, capturing structure cell by cell. Permafrost, in the Klondike, simply refrigerates and seals a carcass against rot. Phosphate, at Bone Valley and in the Cambridge greensand, mineralizes bone and gathers it into dense beds. And a diamond, in the case of Davemaoite, entombs a mineral at crushing pressure, defeating the decompression that would otherwise destroy it. The chemistry leaves signatures. The Vivianite that turned Blue Babe blue forms only in oxygen-poor, iron-rich ground. The golden pyrite coating the Holzmaden fossils was deposited by sulfur-cycling bacteria in that airless seabed. Over and over, the same chemistry that concentrates ore is the chemistry that preserves the dead. Scientists have a name for sites of such exceptional preservation: a Lagerstätte, a German word meaning roughly a storage place, and Holzmaden, the Posidonia Shale, and Cerrejón all qualify. Each method captures a different layer of truth. Anoxia and permineralization can hold shape and even soft tissue. Permafrost can hold flesh, hair, gut contents, and the DNA that lets us sequence an animal dead for 50,000 years. Phosphate holds dense, durable bone. A diamond holds chemistry itself, a phase of matter from a place we cannot reach. Running through all of it is one common thread: rapid burial. A body must be sealed away quickly before oxygen and scavengers can do their work. Preservation, in the end, is luck, and so is finding it before the dragline grinds it to nothing. A haul is only an object until someone reads it, and behind every find on this list stands a scientist who turned ore and spoil into knowledge. Oliver Chowner read the deep mantle from a speck of Davemaoite micrometers wide. Stephen Haggerty looked at Carbonado and dared to argue it was the child of a dying star. William Buckland coined the word Coprolite and showed that fossil dung could reveal what ancient predators ate. The chain runs on. John Stevens Henslow, the mentor who shaped Charles Darwin, recognized the value locked in the Cambridge nodules, and Harry Govier Seeley described the reptiles and pterosaurs those diggings produced. Bernard Hoff spent years perfecting the preparation that revealed ichthyosaur soft tissue at Holzmaden. Edward Binney and Joseph Dalton Hooker first described coal balls in 1855. Georges Cuvier, working with Alexandre Brongniart, proved extinction was real and reassembled vanished beasts from the plaster mines of Paris. In our own era, Jason Head, Jonathan Block, and Carlos Jaramillo brought Titanoboa out of the Cerrejón coal, while Scott Wing studies the plants that rebuilt the rainforest after the asteroid. R. Dale Guthrie read A Bison's Last Hours in the Wounds on Blue Babe, and Grant Zazula works elbow to elbow with Yukon gold miners to rescue the Ice Age before it melts away. A single pattern unites them all. Every one of these scientists depended first on a miner's accident, a chance discovery in the pursuit of something else entirely. Which forces the question what remains unread still sitting in a spoil heap somewhere right now. For all that mining has revealed, what it has not reached is more humbling still. The lower mantle, the layer that gave us Davemaoite, remains physically unsampled. We have held a fragment of it by sheer luck, but no probe has ever gone there. The deepest borehole ever drilled reached 12.2 kilometers, a scratch on a planet whose radius is 6,371 kilometers. We have barely broken the skin, and the mysteries already in our hands stay open. Carbonado's true origin, Earth or star, is still unresolved, and no source rock for it has ever been found. We cannot say for certain whether the Holzmaden mothers died in labor or were emptied by decay after death. We still argue over whether Titanoboa hunted in the water or crushed its prey on land. We do not fully understand why Megalodon, the most fearsome shark in history, finally disappeared. Layered over all of this is a quieter loss. The overwhelming majority of coal, ore, and phosphate is processed without anyone ever examining it for fossils, which means countless hauls are destroyed unseen. The collaborations that do save specimens between miners and scientists in the Yukon and at Cerrejón are the exception, not the rule, and they depend on a miner choosing to stop the machine. Meanwhile, the warming climate is thawing permafrost faster than scientists can recover what it exposes, and a new frontier is opening on the deep ocean floor, where seabed mining for manganese nodules and metals threatens to tear open windows no human has ever read. Every commodity boom is also an unplanned expedition into the past. The cautious truth is that an absence of fossils in a spoil heap is not proof they were never there. The next great haul may already be sitting in a waste pile, waiting for an eye that never comes. There's a thread running through all 10 of these hauls, and it is worth saying plainly. Almost everything we dig out of the earth for value sits on top of or inside the dead. Diamonds carry the mantle. Coal is a drowned forest. Phosphate is an ancient sea. Frozen muck is the ice age itself. We did not go looking for any of it. We went looking for fuel, for metal, for fertilizer, for gems, and the deep past came up with the prize. That is the strange gift of the miner. The same hostile chemistry that makes a deposit worth digging is the chemistry that preserves the dead. So wealth and memory are bound together in the same rock. And the people chasing the wealth are the first witnesses to the memory. What they haul up keeps rearranging our sense of our own place. The mantle, it turns out, is reachable only by accident. A star's death can be mined and sold. Extinction itself was proven from bones pulled out from under a city. The planet keeps an archive measured in billions of years, and we read it in fragments, almost always while digging for something else. The truly disturbing thing is not any single haul. It is the scale they imply, the sheer volume of the past that pours through the crusher every day, unread and unmourned. Deep time is not far away and long ago. It is directly beneath your feet, and we disturb it with every shovel, every drill, every dragline. The ground remembers everything, and every mine is a question we never meant to ask.